Well, somehow it works. Okay, I don't know what happened, but seems like the stream is on live. So yeah, I guess maybe some of you can check whether it actually works on YouTube. But yeah, that's assuming it works. And now start teaching. Okay. Yeah, let's go back to our Fourier transform. Okay. And I guess the review is let's review a few more slides back. So last time we talked about this Fourier transform. So Fourier transform is taking this I should say quantum Fourier transform. So we are taking this classical discrete Fourier transform, which is multiplying a matrix like this, and the exact matrix elements are this e to the ijk divided by n over 1 over square root n. Okay, so we have those discrete Fourier transform matrix, and they're actually unitary matrix. And so if we implement those unitaries as a quantum gate, then that's called the quantum Fourier transform. So we'll transform one quantum state to another quantum state, just like classical Fourier transform to one signal to another signal. Okay, but those signals are now quantum state, and the data of your signal is is the amplitude of your quantum state. Okay, and we see that the Fourier transform has or discrete Fourier transform has this nice product form. Okay, so if your input is a computational basis state, then the output is this interesting state where every qubit is basically a plus state but multiplied by some z rotation. And the rotation angle here depends on your input here. So it's 0.j1, 0.j minus 1, jn minus 1, sorry, 0.jn, 0.jn minus 1 jn, all the way to 0.j1, j2 to jn. And we see in the proof that this 0.jn is basically this j1 to jn times 2 to the minus 1, etc. Okay, this is times 2 to the minus l. Okay, and this is I guess j1 to jn times 2 to the minus 1 and 2 to the minus 2 all the way to 2 to the minus n. So you pull more and more bits to this to the right of your decimal or binary dot here. Okay, and and this breaking notation is for binary. So we'll see this a few times more today. So this breaking notation means we are treating this string as a binary number. So if it's to the right of the dot, then it's times 2 to the minus some power. Okay. So yeah, so we have this thing, and we were able to write down a very fast circuit for quantum Fourier transform, and it's this. So we turn our qubit by qubit into a state of this form. So head mark turn you into 0 0 plus e to the 0.x11, and then you add all those phases with these exponentially small control rotations. Okay? And yeah, so you turn the j1 qubit to this state, and then nothing on here depends on j1, then you can turn the j2 qubit to this thing, etc. And all the way to turn jn qubit to this thing. And yeah, so this works, and it's our efficient circuit to do quantum Fourier transform. And we said that, but you need to be careful. You can do quantum Fourier transform very fast, but that means that a quantum computer can do Fourier transform very fast for you. Okay, it does quantum Fourier transform, and the quantum Fourier transform don't do classical Fourier transform, because when you do classical Fourier transform, you want your input and output vector. And when you do quantum Fourier transform, it's hard to convert your input and output classical vector to a quantum state. Okay? Both convert in and convert out is something that you cannot do efficiently. So so quantum Fourier transform cannot do classical Fourier transform very efficiently in general, but they still allow us to do factoring. Okay, so it's still very useful. And also factoring, there are also several quantum algorithms use quantum Fourier transform. But for now, let's see the biggest application of it, which is factoring. And so now we are building up toward how do we do our factoring algorithm. And I guess they are really, so historical speaking, they are actually two people discover factoring kind of independently. I guess not totally independently, but separately, and there are two ways of thinking. And one way of thinking is this phase estimation because it's easier to explain. Okay? And I guess we can talk a bit about story here. So this quantum factoring algorithm, also called Shor's algorithm, is discovered by Peter Shor. Okay? So Peter Shor discovered factoring algorithm, and the interesting story is that but the phase estimation is not discovered by Peter Shor. So phase estimation is discovered by Alex Kitaev. So maybe let's write down the name of Kitaev. Okay, and who is also very I guess very powerful people in quantum computing. And anyway, Kitaev was not really a computer scientist. So Peter Shor was a mathematician, and Kitaev was a physicist. And Kitaev was in Russia. And when Peter Shor discovered the factoring algorithm, is when internet was not so good. So Kitaev, stuck in Russia, cannot get a hold of Peter Shor's paper. So but he learned that the quantum computer can do factoring very efficiently. So he just derived his own factoring algorithm, and in doing so, he discovered phase estimation. Okay? And so we have phase estimation, which is a nice way to explain our factoring algorithm. Okay, so let's first see what does phase estimation do. So phase estimation is, as we said last time, very quantum very quantum primitive to do. Okay? So this is a totally quantum algorithm, and actually it's kind of go back to a black box algorithm. Okay, so we now will have a quantum black box, and we want to do the quantum algorithm on it. Okay, so our quantum black box is this unitary U here. So we think this U as a black box. Okay, okay. So I guess we should say. This thing is we treat it. Okay, now I need to place my arrow better, so I have a place to write. Okay, so this U we think it as a black box. Okay, and so this is a black box part of the factoring algorithm. Although we will have some explicit U that we'll want to do our phase estimation on. Okay, but for now we think U as some black box is. Just some unitary given to you, you can place in your oracle. But it's a quantum black box because this U doesn't do any classical calculation. Right? So previously we say our U, we have those U sub f that will do on x and y. You will give you x, and you will calculate s of x for you, f of x or plus y. Okay. But now our U here is not this. It's a black box that just do some unitary. Okay, so you have a whole bunch of unitary you can apply to your algorithm. Okay, and so we want to learn something from this black box unitary, and the thing we want to learn is its eigenvalue. Okay, it's something something you always want to learn on a matrix. So this U is a matrix, it's a unitary, and so it's a unitary, so always eigenvalue has this form e to the 2 pi phi, and we want to learn a particular phi. Okay, we want to learn a particular eigenvalue. Okay, and to help you kind of point to which eigenvalue you want, we give you the associated eigenvector. Okay. So so we are given unitary that you can put as a black box to your algorithm, and we have one copy of this eigenvector also given with you, and we ask you to find the eigenvalue. So eigenvalue will be in the form of e to the 2 pi phi, and so So your answer can either be to a 2 by 5, or you can just say some phi from 0 to 1. Okay, it's a sensing. Okay. And yeah, so this is a phase estimation we want to do given this unitary as a black box, and also one copy of eigenvector, then find the eigenvalue e to the 2 by 5. Okay, and yeah, yeah. So here has an assumption. So we'll assume that we are given a copy of this this eigenvector u, or a weaker assumption is, or again, stronger assumption is assuming you can prepare this u. Okay, and also you are actually not given this u as a black box. We give you something stronger. We give you control u, and yeah, also control u to the many times. Good. I guess technically you get control u, you can get control u to the many times this power of 2, but yeah, but this will be a bit more natural. Just know we will use all those control u to very high power. So yeah, in terms of query complexity, our phase estimation is going to be pretty high. Okay. Yeah, so you need to u to some power depending on the precision you want to learn on your side here. Okay, and yeah, so we have those control u, and we want to learn its phase, and let's have a bunch of version of phase estimation. So let's see the very basic idea of how you do phase estimation. So let's assume our phase is the simplest possible phase. Okay, and so this phase, as we know, is any value from 0 to 1. Okay, and really the simplest possible phase to learn is when this phi is 0 or 1/2. Okay, so this is the maximum difference phase you can see on your unitary. So your phase, so is this e to the 2 by 5 is either 1 or -1. So kind of on complex plane, this is the furthest point you can distinguish from. Okay. And in this case, your u psi is, so now this is kind of a go back to our old black box. Okay, so this is like a phase version of black box, where you apply your unitary on your state, you get either nothing happen or you get a minus sign. Okay. So u on your eigenvector u, it either be your original state or you get a minus sign. Okay. And so you can do our phase kickback idea. So this is already getting phase kickback, right? So you see you have this 1 or minus sign. Okay. And so to this phase, you can use the idea just like in our phase kickback to learn whether your unitary u apply a minus sign is you put this plus state in your control register. Okay. And let's just see how this works out. So our input state to our circuit is plus, and our eigenvector u, and then apply our unitary here, control unitary here. So when the control is 0, obviously nothing happens. You still get a 0 tensor u. Oh, sorry, this is I was going to phase. So this plus u is plus is 0 plus 1, so you have 0 u plus 1 u. This is just a distributed rule for tensor product. And then you control u on both of them. So obviously when control is 0, nothing happens. So this is still 0 u. And when control is 1, you get a minus sign, as we said. This is a -1 u. Yeah. And so when this is -1, then oh sorry, when this is 1, then this is a plus or -1, depending on your u has eigenvalue 1 or eigenvalue -1. So this is a plus or minus here. And so when you have a plus, you have plus u as your total state, and yeah. And when you have minus, you have minus u as a total state here. Then you can apply Hedema and do measure and see whether this is plus or minus, just like in our Dirichlet's algorithm. I guess Dirichlet's algorithm. Okay. So yeah, so this is a phase estimation, and you will determine whether psi is 0 or 1 or 2. And if we go back to our binary notation, so you will basically estimate 1 bit size. So if our psi is this bracket 0.j1, so you will determine j1 equal to 0. If this is the case, and j1 equal to 1 is this case. Okay, so this is 1-bit phase estimation. Okay, and yeah, okay, and now I guess a bit of a story time. So phase estimation, and then how do we estimate the size of more bits is when we want to do HOA phase estimation. Okay, and so the funny thing is, I said Kitaev discovered phase estimation, but Peter Shaw discovered quantum Fourier transform. And Kitaev don't actually know how to do quantum Fourier transform. So Kitaev develop phase estimation with a very complicated formula. So it says that well, we can do this to determine the first bit, then we can do something more elaborate, so we can like kind of determine the first bit and do something more to determine the second bit, etc. And all the way to, I guess it's actually the other way around. We can do this by doing U to the many times, and we'll decide less bit, and then we'll decide the second less bit with something more elaborate, etc. And I guess this is actually a homework problem you can do. So I'm not sure it's probably still in homework file. Yeah, so it's a homework file to do Kitaev phase estimation. Okay, and we only ask you to do 3 level, but it's quite complicated. Okay, so homework problem is Kitaev phase estimation. Okay, and yeah, so you can do some I guess some decision tree on your doing those measurements many times, and do a phase estimation. Okay, but here we have a more elegant view of how to do phase estimation, which is we use Fourier transform. So we consider getting all bits of your site together. So we assume site has this form. Okay, so here is assume site has this form. Assume this form. So assume our site, when we write in binary, is just a binary string with some fixed length. So we have a t bit. Okay? So site is TP fraction, and I guess here we have this is a bit of error. So I should say, yeah, this is 0 point this thing. Okay, so this should be some number less than 1. So 0 point J1, J2 to JT. Okay, assume our side as a binary fraction has this form. It's a finite length. Then we do our phase estimation in this form. So we kind of still want to do our phase kickback. So we have a whole bunch of plots prepared up here. And we still have our U here, and we just control U to a different power here. Okay, so you see the first line here is the first line here is what do we do here? We just control U. Okay, control U to the 2 to a 0. Okay, so control U once. Okay, so I guess we should say 2 to a 0 is 1, and 2 to a 1 is 2, and 2 to a 2 is 4, etc. Okay, so on the lowest line here, we control U once, and on the second line here, we apply control U twice. Okay, and then we control U 4 times, etc. Okay, and so what will happen is, well, the more times you control U, you get your phase times more things here, right? So here you got 2 to a 0 times your side, and here you got 2 to a 1 times your side, and here you got your 2 to a 2 times your side, all the way to 2 to a t minus 1 times your side. And so here it goes back to, okay, I forgot number, let's try this. Okay, oh, exactly. Okay, so here it comes back to, no, not right here, okay? So here comes back to, yeah, this form of our quantum Fourier transform. We know our quantum Fourier transform has exactly that form. We have this 0 point Jn, 0 point Jn minus 1 Jn, etc. And those things are actually 0 plus e to a 2 pi j times 2 to a l, with l from 1 to n. Okay, and yeah, so this I guess this j times 2 to the minus l is exactly our this thing, right? This is I guess it's a bit different. This is 2 times 2t minus 1 times 5, but the 5 was 5. We have 5 equal to because 5 is something less than 1 and the j was something bigger than 1. Okay, so psi was like a j divided by 2 to the t, and then if you multiply this, then you have a 2 to the t minus 1. Then you have so here you actually have 2 to the t minus l times 5. So 2 to the t minus l times 5 will equal to you cancel the 2 to the t, 2 to the minus l times j. Okay, so this is exactly the quantum Fourier transform. Okay, and yeah, so here we do the derivation again. We see that this thing is just the Fourier transform of 2 to the t times 5. Okay, and here I'll give a different name. So I guess that's make a name set. Okay, so if our phi is let's say some k. Okay. Okay, some k divided by 2 to the t, and so the end result here is the Fourier transform of the k, and where k is 2 to the t times 5. Okay. And yeah, so if we do this circuit, we get the Fourier transform of what we want to learn. We still remember we want to learn our phi here. And yeah, then we get a state that's the Fourier transform of phi, and then if we want to learn phi, then we just apply the inverse Fourier transform. So yeah, I guess we can skip the middle part. It's really nothing. It's just reinterpreted this result, and anyway, we see that the end result here is we got the Fourier transform of 2 to the t times phi. Okay, and yeah, so the last step of our phase estimation is just apply inverse Fourier transform. And actually, because the phase issue, phase actually works out, you can also apply. Oh, never mind. Yeah, you need to. Yeah, I think you need to apply inverse Fourier transform. Okay. But we know how to apply Fourier transform, so we just do it in reverse. So we can do inverse Fourier transform. And we got this state, we measure it in computational basis, then we learn our phi. Okay. So yeah, so this is our phase estimation. It's we have a very clean representation. And here is we write the phase estimation in even more succinct presentation. So we say we want to estimate some t bit phi. Then we have t here. T here that record our t bit answer. So we have 0 to a t, and we apply gamma to a t. So we get a uniform superposition here. And then we have some register that put our eigenstate here. Then apply. Okay, so the only change here is we combine all those u to u to the k. Okay, and what's this u to the k? Control u to the k here means that. Okay, so this is some notation that we try to define here on the fly. Okay, so we don't have this definition before. So we are saying that, but I think this is quite a natural definition. So we are saying here, here we have a TB string. So here we have a TB string. So it's actually this thing here, but instead of a small n, I should say small t. Okay, so we have some TB string here, and we think we mapped this TB string to some number from 0 to 2 to the t minus 1. Okay. And so this k is some number from, yeah, so exactly here, k is some number from 0 to 2 to the t minus 1, and it's the computational number of computational bases on the upper register here. So if the control register is k, then you apply u to the k here. Okay. And let's see a little bit. That's exactly what this do. Okay, so if your control is O0, you apply u to the 0 here. You don't apply any U. Okay. And if your string here is 00001, then you apply U once. Okay, and then you have a 1 here, and then you apply U twice, and you have a 1 here, you apply U 4 times. Okay, so you see that exactly this binary string will correspond to how many times of U you apply here. Okay, and yeah, so this is more complex notation to write down this thing. Okay, you just think all the thing here as an integer, and as a binary string that representing an integer, and here you apply U to the whatever integer counts. Is a k integer. Yeah, so apply U to a k, and then you see that this notation is nice because then we can write very complexly what is this thing. Okay, so this thing here is well, summation over all possible k here, and then you apply e to a 2 pi I phi. Okay, because each application of a U you get e to a 2 pi I phi, and you have k times, so e to a 2 pi I times 2 pi phi times k here. Yeah, so e to a 2 pi k phi and the U. Okay, and then you face key back, then you see that yeah, this is face, so you can put it on U or you can put it on k. And then you look at this thing and realize that you have some j, and and then if you do inverse Fourier transform, you will just get 2 to a t phi, because you see that when your phi, okay, so if your phi is j divided by 2 to a t, then oh, I guess here I should just write, so we also write begin here, right? So the small begin is 2 to actually 2 to a t, so 0, 1 to the small t, corresponding to 0 to n minus 1. Okay, and yeah, so because in our computational basis notation for Fourier transform with hj go to summation n and sorry, summation k, then this is e to the 2 pi jk divided by n, and n is 2 to a t. Okay, so that's right. Yeah, that's also put here. So begin equal to 2 to a t, and and phi is j divided by 2 to a t. So j divided by 2 to a t equal to j divided by n. Okay. So you just look at this thing and this thing, then you see that they are exactly equal. So you have k phi equal to kj divided by n, and you have jk divided by n equal to kj divided by n. Okay. And yeah, so when you do inverse, you get j here, where phi is j divided by 2 to a t. And yeah, so I guess yeah, I guess here I should also write j here, so it's more fitting. Okay, but yeah, it's a dummy variable. But yeah, here I should probably change k to j. So here this thing, let me make some notation. So I should interchange k to j to fit the notation here. It's a bit less confusing. Okay, let's try to have phi equal to j and j here. Just a small change of notation. J divided by 2 to a t, and here is j. Okay, and yeah, so it's all j here. Okay, and yeah, this is a more succinct notation for phase estimation. So you estimate this phase, which is phi, and it's well, it's j divided by 2 to a t. You can, yeah, you will learn j, and you can divide by 2 to a t to get your phi. Okay, any question on how we do phase estimation so far? Okay, and yeah, that's the phase estimation when your phi is exactly binary bit. Okay, and now let's let's talk a little bit more about face estimation. Okay, so this works, but this has many restrictions. So, yeah, so I guess I should write all those in single slide. But okay, so but this thing has many restrictions. So one restriction is you need this u given to you because you want u here. Okay. And so if you don't get the eigenvector u, how you do face estimation? Well, if you don't have eigenvector u, you don't know how to, you don't even know which face you want to estimate. Okay, but turns out this is actually something we do. Okay, so if you don't get this u, then we can estimate the eigenvalue of a random eigenvector. Okay, and this is actually enough for our factoring need. Okay. Anyway, so if I don't get the eigenvector u, we can estimating random eigenvalue, but we don't get a random eigenvector. So what we do is we put the random state. Okay. So we have just whatever state and put here. Okay. We just put whatever state here and we run phase estimation, and we measure here. We get some phase. And if you work out the quantum superposition, you see that this actually gives you a decent result, okay? Because you have some psi equal to, well, some sum over different eigenvector with some random amplitude here, okay? And you do phase estimation, and okay, so you know phase estimation will say that you put 0 here and u here, and the result is j here and u here. You will get your, I guess depending on notation, so you will get psi here and u here. Okay. And you also, if you have a, if 0 u here, and so you have 0 u, then you get a psi u. Okay. And now instead of u here, you have this superposition of u, and because it's a linear, then you just get the superposition of different u and psi u here. Okay. And when you measure psi u, you just get random psi u with a random u with some random probability au. Okay. And so if you pick your psi random enough, you will just get totally random psi u here. Okay. And yeah, so this is what happens if you don't have the eigenvector, then you pick a random state, then basically you get a random eigenvalue. Okay. So that's one thing. And another thing is, okay, so this is one. And and the second thing is accuracy. Okay. And yeah, so we say our algorithm works if we are in exactly B string. So we are psi exactly this is 0.j1, j2 to jt. Okay, and but what happens if we don't have this thing? Okay, so if our psi is some irrational number, so you can never write in this binary fraction, and they don't even repeat itself. So psi is equal to 1 over square root 2. Okay. And so in that case, our phase estimation will have some error. So this thing we have here is exact. You get the exact phase, 100% probability, 100% correct. Okay. And but well, psi is some number we can estimate to some precision. Okay. So if we have some irrational number, then yeah, 1 over square root 2 maybe it's 0.701 something. Okay. And yeah, so now we can estimate it to some accuracy and with some success probability. And it turns out that those two things are not too bad if you just use enough bits here. So roughly idea is you want the more bits accurate, then you just have more t here. So you just run this algorithm with large enough t, then you will learn your psi to many bits accuracy. Okay, and okay, so the proof is quite the proof of accuracy is quite involved, and yeah, I think it's a bit too technical. The textbook has a proof or all slides have proof, but yeah, but I don't want to go over this time. Okay. But the end result is just quite nice. So the number of bits you use, if you want to estimate on up to n bit, okay, so now it's a bit confusing because this n is different from this n. Yeah. And yeah, but this and t is same as the book notation. So I guess here this n is useless. So let's call this until top. Okay, so this is whatever until top. Okay, and yeah, so if you want to have n bit accuracy, then basically you need to have your t. So the number of bits here basically same as n, but with a little more bit if you want more success probability. Okay. So the extra number of bits is log in 1 raised long. So it's not too much. You can get a very good accuracy with just a few bit aid. Okay. Yeah. So extra bit aid will decrease the error probability exponentially. So it's very nice. You just need to add order log 1 over epsilon bits, and the exact number is here, log 2 plus 1 over 2 epsilon. Okay, so you see that this is not too bad scaling with epsilon. Okay, so yeah, so the result is you want the n bit here, you just have t basically equal to n with a few extra bits, maybe 10, and it will have a very high success probability. Okay, and so that is what you can do. And yeah, the proof is not too hard, but it's a bit annoying analysis, so you can read it up in the textbook if you want to see. Yeah. It's just some mathematic adding things together. And so this is one thing you can do. And also, if you want to just do factoring, another fact about the accuracy you can do is you think about what if you add no extra bit at all. Okay, so if you just do do t bits and want to see how good the t bits are, and it's actually pretty good. Okay, so those two things are different facts about the accuracy are pretty good. Okay, so if you just do t bits there, and actually you will get the basic approximation, means that your result is your phi round back to your t bits. Okay, and with at least this probability, so at least 40% you will get the base rounding you get. Okay, and yeah, so you can also just say, yeah, in our factoring algorithm to prove our factoring algorithm work, because since I'm in NP, you can just check your results, so you can just use this. Okay. So you just use this, and you say our algorithm has a constant success probability. You just try more times, see where you get your correct factoring, etc. Okay. So this is also a fact you can use. Yeah. So anyway, either of this result tells you that factoring is not factoring. The accuracy in phase estimation is an issue, but not too much issue. You just use enough t, and you can estimate your phi to pretty good precision. Okay, and so there's one thing, two thing, and there's a third thing actually down here. Okay, okay. So third thing is query complexity. Okay, so third thing is what are the query complexity of phase estimation. And you think about query complexity of phase estimation is actually pretty bad, okay? Because you say want to estimate up to 2 bits, and how many oracle code you have here is actually 2 to a t. Yeah, so this thing, you think about all those control here, you need to control up to 2 to a t minus 1, and t minus 1 to a t minus 2, etc. So here you actually have about 2 to a t of the oracle code here, and yeah, so our algorithm will scale with t, and so you need the exponential number of u here. Okay, so in terms of black box oracle complexity, phase estimation is actually pretty bad. So you need a lot of black box code to do phase estimation to good accuracy. Okay, so that's bad. But we have some shortcut in when we want to do factoring. Okay, when we do factoring, we actually we can implement this control part efficiently. Okay, so we need to go to the more dirty part of the representation. So we need to go back here. So we say we can do this control u to the k by doing all those control to different power. Okay. And in terms of factoring, we see that those control to many power can actually done efficiently. Okay? So you do this control u to the 2 to the t 2 to the t minus 1. You don't actually need to do some get with size 2 to the t minus 1. You only need to do a get with size about poly t. Okay? And yeah, so that's why we can do factoring efficiently, because this crazy exponential control can be efficiently implemented, and I guess yeah, u to the some j can be implemented with just poly j gates here. Okay, and yeah, so that's the third tricky point about phase estimation. Okay, and yeah, so I guess that's all we want to talk about phase estimation. We can take a break early and come back in 10 minutes, and we'll talk about order finding. So solving actual math problem with our quantum algorithm. Okay, so yeah, let's take a 10-minute break and then come back at 4:25. Change it here.
今天讲完是
应该不会吧？我应该把 order finding 转完就好了，然后下次再加上 show algorithm。order finding 应该就可以讲蛮多的，就是对吧 ？order finding 讲完了，其实 order finding 是不是就很多了？不知道会不会讲完 order finding。order finding 有很多这个 tricky 的 point， 可能会我自己想，看能够讲到哪吧。但其实 order finding 讲完了，factoring algorithm 也快讲完，就是可能会这个 tricky point 再讲一半吧，讲个1-2个。但是这个不 tricky 的 point 应该可以先讲完，就是对啊，可能可以讲到 tricky point 之前吧。我觉得讲到这里还是没有问题的。那在后面的部分不太确定，但是作业可能会那个是不是？还是你等讲完看看决定要出哪里？可以啊，那个，但是其他要不的phase estimation得上吗？哦，对了，这一题。
这礼拜只剩这一题了。
只剩这一题了，其他都做完了。
其他都提到上礼拜去了。
这么快？我有教这么快吗？
进度超强。
哦 ，OK。可以拉一些下个礼拜。那其他 F 那题我记得可以做蛮久，不然你可以把那题变更难一点。算了，那题。
你说这题吗？
只有大家把它全部做完是做得出来的吗？算了，感觉好像困难。我记得那题蛮难的。
这哪一题？这题吗？
比较低级。我记得以前是更难的形式啊，现在是怎样？现在是
就去年的。
他可没觉得啊，你看，我找一下，我记得之前有一个叫大家算3个 beat 之类的，有没有比较久以前的？可以给一个完整版的在一起，我找一下。完整版期末记也蛮难的，好像教大家想办法 estimate 3个 beat， 然后90%的 probability 之类的。类似的。
他不在上次。哇。
我找一下啊。蛮确定有这一题的，可能在比较开始的时代。找一下 QC， 很久以前，这是我 homework 几啊？9的话，2021。2021的9没有这一题呢，我看一下。我想想看，可能在10吗？还是在8？哦，你找到了吗？
应该是
对啊
2022
的，OK， 对吧？可以给大家完整版的。
所以
困难。
这次就
对啊。
完整版80分这样。
完整版，可能也可以不用到80分嘛，也可以吧。你看一下觉得值几分？完整版颇为困难，也没有那么难吧。但是好像比较难的是大家好像不太会做 turn off 的样子，就是这个 probability 哦，有些 probability 要 amplify 的部分。完整版 face estimation 还是蛮有趣的。
那这一块就出这个完整的
哦 ，OK。
可以分，
可以
把后面那个可以分少一点。
完整版，OK。
那就这样。
那完整版不错 ，OK。怎么了？哦。
然后我是打算两个，反正版就打完英文之后交给全体，叫他把所有的都翻译成然后再讲一下。
好，不知道 ChatGPT 的翻译怎样？你要 check 一下。
对啊，
还可以。
但目前这边现在这个应该就是我还没有把 icon 看出来。
没有这样，没有这个。
你觉得那个分类有什么
？OK。
或者是
觉得icon 看起来不太对劲，的确。
还没有选。
OK， 可以选，那不错。OK。
然后
看起来真的是。
然后要有一个是。
是蛮东西，没在不是眼王者。
它本来就是蛮多的，我其实大部分都会被改掉了。还是只会找相关就不会。
这下面是还有什么？
然后可能就是老师也要放历年论文之类的嘛。
可以啊，你论文的话，
就是因为
应该去 Google Scholar 可以找到吧？
能放的也东西也不多，所以剩下应该能放。
看你要放照片，可是大家好像没有照片就是，除非要帮每个人拍照之类的。
叫每个人传照片。
每个人传照片那也可以啊，你可以放成员跟成员照，我觉得倒是不错。可以说可以有个实验室成员的也标吧。
前面还有一个，但我们应该就没有想要放什么实验室的环境之类的。
环境，看你们把它拍漂亮一点。
应该没有办法。所以剩下
需要大门装饰一下。
应该就是，所以除了1、2以外，应该就是历年论文、成员照片跟位置跟联络方式这样。
这样
差不多完整应该是这样。对，那我就，那历年学长们的论文。
学长们的论文可以去那个，可以啊，你可以去那个。你可以给，反正清华都铺上线嘛，你可以去把那个连接一下。
那老师的论文我一定可以通。
可以啊。反正都是公开资料嘛。可以。 Okay. Let's get started. So let's do, yeah. So let's go to go very close to doing factoring. So I want to solve this totally mathematical problem of order finding. Okay. So our input now are just two integers. We have integer x and integer n. And n is something bigger than x, and x and n has no common factor. So the way we write that is the greatest common divisor. So GCD for greatest common divisor. So basically means x and n are co-prime to each other, and yeah, so x and n are co-prime to each other, and x is less than n. So the number we're going to find is if we keep multiplying x. When does x will be equal to 1 mod n? Okay, so the smallest number r, such that the x to r equal to 1 mod n. So this is called I guess the order of x with respect to n. So this order of x is something we want to find. So this problem, order finding, find this order r. Okay. And yeah, so I guess let's actually see an example first. So this is quite straightforward. So you have x equals 3, n equals to 7. So n is not necessarily a prime number, but obviously if you are a prime number n, then you always have x and n will have GCD equal to 1. Yeah. So x3 and n equals to 7, and well, the simplest, the brute force way to do this order finding is just you keep multiplying x by itself. So you can have what is x2? x2 is 3 times 3 equal to 2 mod 7. So it's 9, but you mod 7, it becomes 2. Then you have x third, so now you can just have 2 times the x. Okay, so 2 times 3 equal to 6 mod 7. Then x4, you have this 6 multiplying your 3, and it's 18, so mod 7 is 4. 4 times 3, and it's 20. 20 mod 7 is, sorry, I cannot do multiplication. 4 times 3 is 15, and it's 12. 4 times 3 is 12, and 12 mod 7 is 5. Okay, and finally you have 5 times 3, and yeah. 5 times 3 is now it's actually 15, and 15 mod 7 is 1, and you have r equal to 6 here. And yeah, I think there is actually some mathematical lemmas that if n is a prime, then r will be a minus 1, etc. Okay, but we don't care about that. We just care about definition of r here. Definition of r is how many times of x you need to multiply with itself to get this equal to 1 mod un. Okay, so this is the order. Okay, and obviously, and I guess now you actually need some mathematics. So the mathematics here is that r always exists if x and n has GCD equal to 1. Okay. And yeah, it's not too hard to show. So, but here we just say the r will exist if this thing happen. Okay, so every xn you can find there is this r. And we just see the classical algorithm. So classical algorithm to find this r is well, we don't really have a lower bound, but we haven't found any efficient algorithm for this. So we want to solve this, then we need to have about polynomial in n. Okay, and now let's say a little bit about the problem size. So the problem size here, we actually think about is the problem size is how many bits does n have. So how many bits do you need to write down n, and it's about log n bits. Okay, obviously. And so this L is problem size. And the classical algorithm, basically we only know the brute force algorithm, so you just keep multiplication. Okay, and at some point you hit this r, and yeah, so this algorithm you need to do about 2 to L steps, so basically about n steps. Okay, and there is no non-classical algorithm that do this very fast. Okay, and we'll see that the quantum algorithm we can do order finding by doing phase estimation, and we will solve this problem in time about order L cube. Okay, and yeah, and So this is where the quantum algorithm can solve a factoring very fast, because it was already known to mathematicians that if you can do order finding very fast, then you can do factoring very fast. And in terms of computer science, we say we can reduce factoring to order finding. Okay, yeah. So this is the problem we want to solve. We want to have our quantum algorithm solve this order finding problem. X to the r equal to 1 model. Okay. And so how does our quantum algorithm work? And I think the main part of the algorithm is actually not too hard. The main part of the algorithm is you want to do phase estimation on this application by X unitary. Okay, so you think you control a quantum circuit that do this unitary. So I guess you should have like a double highlight here. The highlight here is this UX. Okay, so the important thing about here is thinking about this UX, which does multiplication. Okay, so multiplication is multiplication model is a classical computation you can do, and you can do that in a quantum circuit. And I guess technically it's a bit more complicated than this, because this is in-place thing. But anyway, so yeah. But for now, let's just assume this can be done. Okay, there are a bit more, yeah. There are a bit more detail on whether UX can be implemented efficiently. But for now, let's assume this can be done. Okay. So this is a side mark that I guess we can fill next time. Yeah, there are tricks to get around this. Okay, we apply UX efficiently, and yeah, I guess to implement UX efficiently, the problem is this is what called in-place oracle. Okay, so if you just have y and yeah, let's do digression a little bit. So if you have some y and you want to implement multiply by x, then we know our usual quantum oracle we do is we will have a ux and a y and some z register, and you can have y and x, y, or plus z. Okay, so this is pretty standard. But if you want to erase your y information, then it gets more tricky about how to implement this UX here. Okay. But let's ignore that for now and think about what we can do if we can implement this UX efficiently. Okay. So we have this multiplication oracle, in-place multiplication oracle, and you will take a number and multiply it by x and model. Okay. And yeah, so technically this oracle exists because this is a one-to-one relationship. Yeah, because so it's this line here. Okay, so because our GCD of xn is 1, so actually so basically you want this thing to be reversible, so you want to have ux minus 1 exists, so basically you want to divide by x model also exists. Okay, and GCD xn equal to 1 ensure that this thing happen. Okay, and yeah, so that's our weird unitary here. So is multiplied by x unitary. So multiplied by x unitary, you actually on some computational basis y, you get basically sy here, and everything is modeled. So so this x and y should be your number between 0 and -1. So we are doing everything modeled. Okay. Okay. And yeah. Okay. So more points here. So ux is n by n unitary because it acts on a space of size 0 to n minus 1. Size of a space of size n is 0 to n minus 1, and they output something 0 to n minus 1. And actually x cannot be 0, so it's actually from 1 to n minus 1, but that's okay. Okay, so we're okay with this ux, although it's questionable that whether you can apply this efficiently, but people have worked out this thing. Okay, so there is a workaround on how to do something that similar to this. Okay, and yeah. Okay. And so back to order finding. So what is our order finding algorithm is we want to do phase estimation on UX. Okay. And yeah, so phase estimation on UX, and what is phase estimation on UX, then we'll find the eigenvalue of UX. So let's ask us about what are the eigenvalue of UX. Okay. And there are many eigenvalues of UX, but particular eigenvalue we care about is eigenvalue for states that look like this. Okay, and yeah. And yeah, so UX is n by n matrix, so there will be n different eigenvalue. Okay, but we'll actually only take about R of the n eigenvalue out of it. Okay. So we'll take R eigenvalues that are related to all those power of x. Okay, so think about those states. We will control some pretty specific eigenstate of the UX. Okay, so let's think about you can have a state that's equal superposition of all those power of x. Okay. So it's x and x cube, x squared, x cubed, etc. all the way to x to the r. And we know x to the r equal to 1. Okay. So in terms of this, then we have, well, actually everything here. Okay. And yeah, so suppose we have this state, and yeah, and yeah, we omit the normalization. So we have this state, and we apply okay, so here we have the wrong writing. So I should not write U1 here. Okay. So suppose we have this state, and last thing what is eigenvalue. So you apply UX on it, and then this x becomes x squared becomes x cubed, etc. And xr minus 1 becomes xr, which equal to 1, and xr equal to 1, and 1 times x becomes x. Okay. And yeah, so you see that you apply UX on this thing, you just cyclically permute all those bases, but this addition don't care about ordering, so you just go back to US and U0. Okay, so you see that this state has eigenvalue 0. Okay, and that's not too interesting, but we can have this state with some modification. Now this is kind of similar to the Fourier transform ideas. Okay, so we can add some omega, where omega is R root of 1. So let's assume omega is this, well, actually R root of 1 with negation. So 2 minus 2 pi I divided by R. Okay, and we add some, we multiply some power of omega. Oh, sorry. Okay, so I auto battery. Okay. And yeah, so we multiply some power of omega in front of all those x power. So let's say we have u1 equal to omega x, omega square x squared, etc. And all the way to omega to the r xr. And remember omega to the r equal to 1. And then apply ux on this thing, then you will cyclic shift all those x here. Okay, and then you see that we are getting, so basically what we get is we get a different power of omega in front of our x. And so what we get at the end is you just get this omega minus 1 phase in front of our u1, because we have shift all those x. Okay, so we have x to a 1, 2, 3 to r. Now it's 2, 3 to 0. And then it was omega squared here, and it become omega. And yeah, it was omega here, and it was actually 1 here, etc. Okay, so we get omega minus 1 vector. Okay, so the eigenvalue is actually omega minus 1, which is this e to the 2 pi I divided by r. Okay, and so here you see the phase here is 1 over r. Okay, so psi equal to 1 over r for this u1. And similarly, you can have u2 equal to more power of omega in front of your x. So you have omega squared, omega fourth, all the way to omega to r minus 2 times r minus 1, 2 times r, etc. And then you apply u on this, you will get, so okay, so you apply ux on u2, then you will get omega to the minus 2 on your u2. Okay, so your psi will equal to 2 over r, etc. Okay, and yeah, so this is where we get our r in from our phase estimation. So say if we get our u1 as an eigenvector, then we do phase estimation, we'll get 1 over r, then we'll learn over r. Okay, so remember we want to learn over r. Okay, so yeah, so this is very cool. This is what we want to get. Okay, so if we can get a u1, and then we can just do phase estimation of ux, then we'll get 1 over r. Okay, okay. And yeah, let's write all these things in more complicated form. So all those u1, u2 to actually all the way, we can write this up to u to the r minus 1. Okay, and up to u of r minus 1. So let's write this in a compact form. So we define this u sub s. So s is something from 0 to r minus 1. So just this u sub s here. S equals 0, s equals 1, s equals 2. Okay, so u sub s is no actually right normalization. So 1 over square root r, because there are different computational bases stay here, and sum over different sum over k from 0 to r minus 1 x to the k model. So all those xk, and we have this omega phase here. So here is omega to the s times k. So it's e to the 2 pi e to the minus 2 pi divided by r. This is the omega part, and times s times k. So remember, s is this s here, and k is this k here. Okay, so here, say here we have s equal to 2 and k equal to 2, etc. Okay, so yeah, e to the s times k. And then you can do this checking here, this ux on us, but just algebraically, and you see that ux on us, you increase this k to k plus 1, because just multiply everything by x, and then you relabel your k, then you get hr e to the 2 pi s over r phase. Okay, and as we said, then if you do phase estimation on any of these, when s not equal to 0, then you will learn s over r. Okay. Okay, so that's pretty cool. If you can get a hold on some us, then you can learn this s over r, then you will learn your r. But I guess that's a basic idea. But now there are many hurdles to overcome. Okay, and now this goes to our what happens when you do how you do phase estimation when you do have an eigenvector. Okay, say maybe we can construct the eigenvector, but basically if you want to construct us, you need to know r. You need to know all those. So intuitively, you want to know all those things, and then create a superposition of them. But you already know all those things, you probably already know r. Okay, so yeah, creating us is probably not going to work. Okay, and okay, so here is yeah, a bit of a thing that we don't need. So just a bit yeah, more result on those omega. Okay, and okay, and how do we get the us is well, we cannot control any us, Okay, so this is actually for this. So we cannot control any US, but we can now control a superposition of all US. Okay, so it turns out if you add all those US together, then it becomes a very simple computational basis vector is one vector. Okay, and now that comes from this slide. Okay, so I should put this on next page. Okay. Come from this slide because maybe let's look at this here. So you see that the face will face on x to a 0's power, fixed on this x to a r, or x to a r be equal to x to a 0. Okay, fixed on x to a 0 is always a 0. Okay, because it's omega to the r to some power. Okay, omega to the r, omega to the 2r, etc. Those are all equal to 1. Okay. So on the one on the one component or x to the r component, this face here is going to be omega to a 0. Okay, so that's on the k equal to 0 component. You have omega to a 0, and all those omega 0 to a 0 add up, and yeah, so add up all those US, it become add up all those US, and it become excuse me, it become 1. Okay, and what? Well, with some normalization. Okay, so there are actually different US, and yeah, you normalize the adding by having this 1 over square root r, etc. Okay. Okay, so on the one component, they all add up, and on other component, then this thing happens. So you will have the face all over this circle, and they will exactly cancel out, and you get that when you add them together, the face becomes 0. Okay. So I guess the derivation is the thing we want to use is this, but the derivation we want to say is the other way around. So we want to say some s from 0 to r minus 1 US. Equal to square root r1. Okay, so the one component get the square root r, and all other component cancel out because they are spread around circle, just like this thing we do in discrete Fourier transform. Okay, and yeah, so that's very cool. So what do we do instead of phase estimation on US? Is we do phase estimation on 1. Okay, so we have 0 and 1. We do phase estimation. Then we will get random s over r. Okay, so we don't get totally random. So it's a little bit different than what we talked last class. We say we will get a totally random vector here. Then we will get a totally random phase out of the n different phase. Okay, so we don't actually do that. We do 1 here. Okay. And we put 1 here, we do phase estimation, and we get a uniformly random s over r here. Okay. So yeah, so we can get a uniformly random s over r if we do phase estimation. Okay. And yeah, so we'll get s over r with uniformly random s. Okay. So this basically allows us to do order finding. And yeah. Okay. Okay. So here is a sketch of our order finding algorithm. We'll have our black box unitary. This u of x actually also depend on n, so that's right here. So u sub xn, and this black box will do this multiplication. So ux on y equal to xy mod n, where yeah, and with l equal to log n. Okay, and yeah, and yeah, then we will want to find the smallest r such that x to r equal to 1 mod n. Okay, and the idea is that yeah, I guess here we don't write too much. So here is like an algorithm sketch, but really just we say we do phase estimation on this black box. Okay. Okay, And yeah, but here we just calculate out all the detail of phase estimation, but really nothing new. So we calculate the detail when you do phase estimation on 0, 1. So phase estimation, it has 3 steps. So you do head map to a T on first register, then you apply your control unitary. So control on first register J, you do control unitary, and you will get this HR phase here. Yeah, so we're writing this one as a sum over our eigenvectors, and so you can express your u as you get a phase kickback here, and then you do quantum Fourier transform, then you will get some estimation on your S over R to the T times your S over R, but there is yeah, some estimation on to the T times S over R, and yeah, you measure first register, then you get this S over R. Okay, and so this is the phase estimation part, and okay, so I guess the quantum part is this phase estimation, and you will need to run many times, and you will get many different S over R. And then you know your T, so you can divide by 2 to the T, you get some S over R. And you get the uniformly random S, and but you get uniformly random S, and you ask how you get random all those S over R from get R from those random S over R is you need to actually run this procedure many times. So you need to, so it's a bit like a Simon's algorithm. Every time you get something that's perpendicular to your secret string, and you need to run many times. And so yeah, similar to that, you need to run your order finding algorithm, this phase estimation part many times. You get many different S over R. Okay? And you do this many times, and you get different S0 over R0, S1 over R1, etc. And you can get your R by calculating the least common multiplier of all those denominator here. Okay, so that's a sketch of order finding algorithm. And but I guess stop here for now a little bit. Any questions so far? So yeah, so the big idea is you want to do order finding on these states. That's a superposition of so-called I guess that's right something more, but it's a nice name for some concept actually pretty easy. So we will do order finding on this superposition of orbit of X. Okay, so orbit of X in terms of group theory is just you will keep applying the selection over and over and see where does this X go. So you see if you apply multiplying of X, keep multiplying X on 1, then you get this orbit of X. And yeah, it's X squared, etc. Okay, so you get this superposition of orbit of X, and you see that there are very nice eigenvector of your multiplication unitary, and they have this eigenvalue. Eigenvalue basically phase S over R, and one this Ket1 is equal superposition of them. So you do phase estimation on Ket1, you get uniformly random S over R, and you have enough S over R, then you can learn your R. Okay. And now let's talk about tricky point of doing this. Okay, and I guess we'll go through 1 or 2 of them, but let's first explain why they are tricky point. Okay, and I guess we already solved the third tricky point, so let's say this. Okay, so first the third tricky point is that S and R might not be coprime, so you just get one of S over one. You just get one S over R, one pair of SR. Then you don't actually get a pair; you get a fraction, right? You get a fraction because when you do phase estimation, you just get a number. You get a number S over R. Okay, and say your R is not necessarily a prime number. R can be something like 6. Okay. And if R is 6, you can get S equal to 2. and you get 1 over 3. Then you don't know r is 3 or r is 6 or r is maybe actually is 3 over 9, etc. Okay, so you get 1 over 3, you don't really know r. Okay, and that's why we need to do this multiple times. Okay, so we need to do this multiple times, and we did this common multiplier. Then you can do some number theory and show that with high probability, you don't need to take too many of them. You take constant number of them, and they will have some constant probability to get the correct r, no matter how big r is. Okay, so that's pretty cool. So that's SR not coprime. Okay, and then there are two other things, and I guess actually the second one is probably more obvious. You need to think about. Okay, the second one is we all talk about those kind of in the phase estimation, but let's look at it more carefully. So second one is phase estimation has some precision. Okay. And S over R you will estimate with some error. You will not get precisely S over R. Say, maybe this example once again. S over R is 1 over 3, then it's not a fixed length bit string. Okay, and and when your R is and the happen when r is not divisible by your n equal to 2 to the t. Okay. The other way is when n is not divisible by r. Okay. So basically, when r is not the power of 2, your estimation of S over r will have some error because r is you get r is not power of 2, and you also only estimate this fraction in terms of 2 exactly. Okay, and you get some error, and we say error is okay, but because you can truncate somewhere, but then you think about truncate 1 over 3 to but here is something extra. So although we do this in binary, let's think about this in decimal. So this 1 over 3, you get something like 0.33333. Okay, so you think this looks really like 1 over 3, but how do you tell a computer to say this is actually 1 over 3? Okay, and so this is something actually, but actually we can do this with the algorithm, and we can do this with so-called continued friction algorithm. That is, you can determine some accuracy. So maybe you say up to 10 to the minus 5, and then you see a string like this. Then you will find out that some close rational number is actually this 1 over 3, etc. Okay, so so this is a problem with our accuracy. So S over R might not be an integer, and we have some truncation error. Then how do we get rid of the truncation error? Okay, and finally we have the problem of we want to do this multiplication efficiently. Okay, so we said that we actually do a lot of call of UX. We do exponential number call to UX. Okay, so now here T is we estimate this to T bits, where T is about our big N. Okay, and we don't really want to do the T calls to this multiplication unitary, because if you want to do that, then that's basically just same as doing the classical algorithm of multiplying everything. Okay, and so here is kind of where the quantum algorithm get the exponential speed up. Is we can do this oracle of u to 2 to a j very efficiently by doing repeated squaring. Okay, so if you want to multiply x by some 2 to a j time, you don't actually multiply x that many times. You can keep squaring x. Okay, and let's see this repeated squaring working. Okay. So if you want to calculate what's x to the 2 to the j, then yeah. Yeah, you can do this with only OJ multiplication. Okay, and I guess we don't need it usually. Okay, and yeah, so what you do is you don't keep multiplying x, you keep square your number. Okay, so say x squared equal to x times x, and when you do x to the 4, you don't need to multiply x 4 times. You can do x squared multiplied by x squared. And all the way to x to the 2 to the j is x to the 2 to the j minus 1 times x to the times 2 to the j minus 1. Okay, so you only need to do j multiplication to calculate x to the 2 to the j. Okay, and okay, and yeah, and if you count all the number of gates you need use exactly, then you need to use the order L cube operation to do this. Okay, so here is a bit of counting, and yeah, I just say the result, and here is here is the L cube operation you need to do your quantum order finding, and it's to do your repeated squaring. Okay. And yeah, so instead of because you can do repeated squaring, so instead of multiplying 2 to the L times, you only need to do multiplication of L cube times. Okay, and here is a bit of example. So x to the 16 is x to the 2 to the 4, and you only need to do 4 multiplication to calculate x to the 16, and that's improving from 15 multiplication by doing all multiplication. Okay, so yeah, so this is kind of where we get our exponential speed up of I guess there are many different interpretation of where the shortest algorithm getting exponential speed up, but this is one way to look at it, because you only need to do in our quantum algorithm we do things in superposition kind of, and so this multiplication we do multiplication by only need to do basic multiplication with this power of 2, so we can do multiplication by repeated squaring, and this multiplication is yeah, much faster than doing brute force multiplication. Okay, so that's the cool part. Then that's the cool part where we have a cool answer, and now then we have the more dirty part of the problem need to solve. Okay, so now the other part is not really related to quantum. We just need to find a smart classical algorithm to solve all those edge issues. Okay, so first problem is we are now given some truncated S over R, and how do we find the S over R? Okay, and I guess we don't really get a proof here, but give idea of how the algorithm run. Okay. I guess in our homework, probably not this week, but maybe next week, there is a homework that yeah, prove that this thing actually works. Okay, kind of works. And but anyway, let's see how the algorithm give you an idea of the algorithm, the constructive part. Okay, so let's say we have a number psi equal to something like this, 0.25001, and this looks really like 0.25. And yeah, how do we ask the computer to say this is 1/4? And what we do is we ask the computer to calculate the continuous fraction. So we have this 25001 divide, this thing is 25001 divided by 1000000. And we flip this around and become 1 over this 1 over 1000 divided by 25001, and we will divide this is 3 plus this weird number 24997 divided by 25001. Okay, and then we flip this fraction part again, and it's 1 over this 25001 over 24997, and it's this now it's 1 plus 4 over 24997. Okay, and at this point, your computer will say this fraction part is very small, so basically you will set some threshold on your fraction part, and then you say the fraction part is very small, then we just discard it. Okay, and because it's very small, we discard it, we don't change too much. Okay, so we change this to 0, and then we compute everything back, and then we see that this is 1 over 4. Okay, so that's the idea of the continued fraction algorithm. You have you just you have a fraction less than 1, and you flip it, it becomes something bigger than 1, and you take all the integer part and the remainder part, and they become some fraction less than 1 again, and you keep doing this until your fraction is very small. Okay, and when your fraction is small, you just throw it away and roll everything back, and you will get a fraction number that's have a decent number here. Okay, so that's the continued fraction algorithm. Okay, and yeah, you can have this in general to any number. So you write this with some a0, then yeah, you can have continuous fraction for any number, not just a number less than 1. Okay, and yeah, that's the continuous fraction algorithm, and we don't have exactly proof how it works, but we have a kind of proof. Okay, so yeah, so I guess the theorem of this working is this thing. So if our so S over R is the thing we want to estimate, and if we have well, this is the exact thing we want to this is the fraction we want to calculate, and we have some estimation of S over R, and let's say they are very close. They are close up to this order R square factor. Okay, so we want to have our psi calculated to very pretty high precision. Okay, and we want to have it pretty high precision, so you see the precision is actually R squared, so about N squared. Okay, so actually we need to calculate psi to very high precision, so maybe 2 bit. Okay, and we have this precision. I guess it's 2 bit, but it's still order L, right? Okay, so it's not too much trouble. Okay, so still order L bit. Okay, and yeah, so we can find the S over R in continuous fraction of phi by cutting off at the order L levels. Okay, so basically you want to cut off at around this area, 1 over R square area, so probably 2L or 3L. Okay, yeah, so oh, I guess this is a different cutoff condition we kind of say here. So actually the theorem here says we can cut off instead of looking at what's the difference here, we just cut off at how many level we run. Okay, so we just run this with enough level and throw away, go back, and yeah, we'll get our S over R. Okay, and our homework, we have semi-proof of this factor. Okay, so I think we will prove that you can find something. Yeah, I think the homework says that if the error is small enough, then whenever you find S over R, there is a unique S over R. Okay, it's quite simple. It says that if it's measure psi to enough precision, then yeah, you will find you have psi to enough precision like this. Then the S over R you find whenever you can find the S over R close to your psi, then it's a unique S over R. So we prove existence. Okay. And anyway, so here is a theorem that without proof, just say that this works. And to get this, then we need to have our phase estimation to enough precision, and we just tune parameter. So remember, in our phase estimation, we can say we just make T bigger to have more bits of accuracy. Okay, And here basically we need 12 plus 1 bits of accuracy because we want the 1 over 2 R square error. And here, yeah. Okay, and because R is less than N, less than 2 to L. Okay, so R is less than 2 to L, so 2R squared has less than 2 to L plus 1 bits. Okay, and yeah, so we want 12 plus 1 bits of accuracy, and then this works out. Okay, and yeah, so just you pick your T is bigger than this, and then you add a bit of a log 1 base on base extra, and you can face estimation here. Okay, and yeah, so T equal to 2L plus 1, and yeah. And yeah, and repeated squaring have this L cube thing. Okay, and we have a bit. Let's see, order finding and sorry. Oh, here is example. So theorem and you have about 10 minutes, but I think it's but we I guess we start early, but I think we can yeah, we can probably leave it here for now. Okay, and yeah, so next time we'll talk about a bit of proof of why this getting many S and R works. Okay. And yeah, here we have a bit of well, here is just number theory. Number theory tells you that you get random S over R, and then you get enough of those R1, R2, and you get less common multiplier. Actually, you only need 2 of them. You can get many of them, and it will give even better probability. But actually, if you just get 2 of them, you will get the correct one with probability at least 1 over 4. And that's just how much we want. We want the constant success probability, then we can do our factoring algorithm. And I guess we don't need to go all the way to factoring, right? We can do order finding. Then with this R, then we can just do repeated squaring and calculate x to the R. And yeah, you can just check whether your x to the R mother n equal to 1. Okay. So yeah, so with constant probability, then you just try this, and if it doesn't work out, just try this about 4 times more, and they will get you a correct R. Okay, and yeah, let's stop here today, and next Tuesday we will finish the proof, etc., and then talk about the actual factoring algorithm. Okay. Yeah, but the most quantum part, we already see the most quantum part of the factoring algorithm is this order finding algorithm, and it's done by face estimation on multiplication, the multiplication oracle or multiplication unitary. Okay, so yeah, see you on next Tuesday.